Alright, here we are back for part 3 in the final, hopefully, section here. We talked a little bit about diffraction on the last one. Refraction, we said, basically the longer the wavelength, the better it diffracts or bends around things. Okay, and this has something to do with why we see orange and yellow sunsets, because those wavelengths of light diffract better than some of the others. Also, it has, like I said, well, AM radio station waves bend around buildings better in town and stuff, and because of the diffraction going on, they have longer wavelengths than the FM, and so they diffract around the buildings, and it's better to hear them. All right, now, new topic is I think on your paper, but anyhow, interference. All right, this is when someone's trying to catch football, someone gets in their way and get flagged 15 yards, or I forget, or is it holding? Anyhow, one of the times that the interference happened, I forget. But anyhow, it's been so long since we've seen football games, right? Or any sports for that matter. So, let's get back to interference. Basically, interference is basically when two waves overlap and form a new wave, okay? It's kind of like, not a band, new wave band, that's a different kind of new wave, but it's kind of like when two football players try to occupy the same space, catching the same football. Okay, well, in this case, you have two waves in the same spot, and they interfere with each other. Now, that can be good or bad depending on what you're trying to do. So, for example, here is a example of two waves. Okay, here we have two waves that are both going up at the same time and down at the same time. Okay, so in this case, we say that they're in phase, or think about it as in step. Okay, they're in phase or in step because they're both going up at the same time. If they overlap with each other, they're going to make a new wave that's even twice as tall and twice as deep down at the bottom. It reinforces itself, okay, and so you actually get a stronger wave, or if it was light waves, it would be a brighter light or whatever, okay? If it was sound waves, it would be actually a louder sound, although sound waves are not transverse waves like this. We'll look at an example for them in a minute. But if they're in phase with each other, they're both going up and down at the same time, they will actually reinforce each other and give a greater amplitude, okay? And we're going to call this constructive interference, okay? So this is going to be constructive, or making a bigger wave overall. So this is going to be constructive interference, okay? And it actually reinforce each other. On the other hand, if the waves are out of step, this one's going up and this one's going down, this one's coming down, that one's going up, now they're going to cancel each other out, because if you add these two waves together, they cancel it out and you end up with a straight line. Okay, nothing. Okay, they basically erase each other, auditorially speaking, I guess. All right, now this is not constructive, then this is going to be destructive. All right, so this is destructive interference, okay? And so this is when they cancel each other out or subtract from each other. And in this case, we would say the waves are out of phase, all right? Now, which one is better? Well, it just kind of depends. If you, for example, were trying to make a light brighter, then you would want the waves to be in constructive interference, or if you want a sound to be louder, okay? Let's look up here as the example of the tuning forks and see how this applies to sound. Remember, sound waves are compressions. Instead of the little lines, they're using these little dots showing how close the molecules are being shoved together, which is really what happens. When you hit the tuning fork, it vibrates. When it vibrates this way, it pushes these atoms together, and they spread out, and they close together and spread out, and the vibration passes on down. Okay, when it goes the other direction, they spread out, and so you get this pattern of compressions and rarefactions, compressions, rarefactions. Now, in areas where they don't line up with each other, the compression here is lined up against a rarefaction, and we have a train going by in case you haven't heard. They're canceling each other out. That would be destructive interference. If this happens in an auditorium, for example, you have different sound waves bouncing off the walls and they cancel each other out, you're not going to be able to hear the concert very well. On the other hand, when they line up with each other, that is constructive, and that makes a louder sound. Then when they're not lined up, you get destructive, still mostly destructive, and then they're constructive again. Okay? Now, like I said, it can be bad if it's canceling out sounds. It can be good if it's making them louder. And usually when you have different instruments in a band, instead of two of these forks, the same thing, it actually makes the beat. The on beat, off beat is where you have constructive interference between the instruments, making a louder sound and a softer sound, and that's part of what gives music the beat to it. Now, another example of constructive destructive interference would be noise canceling headphones. Okay, in noise canceling headphones, what actually happens is they have a little microphone that picks up outside noise. Okay, and it says, oh, this is what the noise is outside your headphones. And what it does inside, it creates a noise that's kind of like the anti-noise, the opposite of that one. And so it cancels it out. And so what it's literally noise canceling. It hears the noises on the outside. It creates a noise that's kind of like the opposite or destructive interference to that sound. And when you add them together, then it cancels it out, and you don't hear any noise except for your music. Now, what if the outside noise is the same frequency as some of the music you're listening to? Will it get canceled out? It could cancel that out also. But usually the good news is the music you're listening to is not going to be the same frequency as the kind of sounds that are out in the outside world. So that's actually what it will do. It'll cancel this noise so you don't hear it, and it will just let you hear your example here on YouTube. Since I can't demonstrate this for you, they're going to be moving this back. That there's a node right here in the middle that stays in place. When the wave goes and vibrates off this other side, it comes back and vibrates in the same way, so that you have standing points here, which are the nodes. We'll put them back on there in a minute. And that means it stays still and goes up and down here and there. There's your nodes. And then these others go back and forth, back and forth. Okay? And if you do it faster and faster, higher frequencies, it will get more, up to 5 or even 6 later on. And these are caused by this wave going this direction, bouncing back or reflecting off this side, and interacting with each other, kind of reinforcing each other. Okay? These are called standing waves. Okay? And so a standing wave is a wave pattern in which two waves are equal in wavelength. They have to have the same wavelength, and they have to have the same amplitude. And because one of them's reflecting back and the other one's going one direction, they're going in opposite directions, and they're constantly interfering with this. And these are called harmonics, and they are important in music, okay, in sounds and stuff like that. We'll talk more about that maybe when we get to sound. But these are what we call standing waves, all right, and they look kind of the same. The simplest is where you have one wave goes up, and then when it reflects off going down, it just goes back and forth. And when you look at it from the side, it looks like this one pattern. If you do the second harmonic, then that means you have two of them, which has a node here in the middle. This is node, N-O-D-E. I know that was the right answer, and I know you know that already, but there we go. That's the node. All right. Where it gets the highest spot over here, that's kind of the opposite of the node. So that is the anti-node. All right, and we will talk. Yeah, so you need to know those. The nodes are where they come together. So this would have a node here, and a node there. So that's 3 nodes, all right, which makes it a node-it-all. And then you have 2 anti-nodes, one here and one here. Okay, and here would be with 3. Okay, so you would have a total of 4 nodes and 3 anti-nodes in order to make that one. That would be like the third harmonic and so forth. Okay. So those are kind of what standing waves are, when they reflect back and they interfere with each other, but they're the same amplitude and wavelength, and so they don't destroy each other like they normally would if it was destructive interference. In fact, they can actually work where they are constructive interference and make a louder noise. We'll do demonstrations of that later. And last, about resonance. Okay, resonance is it has a natural frequency which it wants to vibrate. Okay, and if you can hit it with vibrations that are at that same frequency, it will cause the object to naturally start vibrating. For example, you've probably heard of the examples of people singing with a glass, and they sing and hit a certain note, and it makes the glass shatter. And what happens is, if they can sing at the right frequency, it's not necessarily how high the frequency is, it has to be the glass's natural frequency. Waves hit it at that frequency, it wants to vibrate. And when it wants to vibrate, it begins to vibrate, and if it vibrates strong enough, glass being semi-solid, will shatter because it just can't move that much. It starts to vibrate too much, basically, and it shatters the object. Okay? And so that is the natural frequency. And resonance sorry, I didn't mean to yell at you in capital letters there for a second, but ability of an object to vibrate by absorbing energy that hits. Okay, and so when vibrations hit the object with that natural frequency, if you have a wine glass, which I had some at school, but we'll see, maybe we'll get to this on the video, but if you put water in it, and then you lick your finger and wrap it around, rub it around the top, it will start vibrating or humming. You've seen singing glasses before, that's basically what that is. And it's because you're vibrating at the natural frequency of the glass, so the glass starts to vibrate and making sound. Alright, so that's basically resonance. Now, let me see if I can find a couple of videos online since we showed mine. And here we go. Thing here. First, he's going to rub his finger on the top, and that finds the natural frequency of the glass. Now, he has a speaker that's picked that up, and now the frequency, and obviously the louder it is, yes, it will make it vibrate more, but it has to be the loudness, it has to be the correct frequency. They get a little shrill when they jump, so you have to turn it down. You can see it shaking, vibrating. Our strobe lights, so you can see, do it in slow motion and all. But basically, you can see how you have to have the right frequency that makes it vibrate, then you amplitude so that it makes it vibrate enough that eventually it can't break that fast, shatters in little pieces. Something to work on during the break. You can figure out if you can do that on your own. Anyhow, that's it for the wave notes, and it's been real, it's been fun, but see you next time. Bye.